Welcome, everyone. Thank you so much for joining us today. I am Jessica Rodriguez, the Industry Engagement Outreach Officer for the Data Science Institute. And welcome, and thank you for joining us today for our iCubed. iCubed stands for Institute, Industry, and Innovation. These seminars connect our industry affiliates to our students and the larger Columbia community to explore topics at the forefront of industry. We invite data scientists, engineers, or researchers from our affiliates to give talks about a recent project or case study. During these educational events, we encourage attendees to ask questions via the chat feature. Today, we have data scientists from JP Morgan. Today's talk will be Visual Perspectives in Finance, and we are joined today by two members of the AI research team, Zeng and Srijan Sood, both of which are AI research scientists in the AI research team. Welcome.
Thank you, Jessica.
Thank you, Jessica. So, hi, everyone. We're really glad to be here. So today with me, I have my colleague Zhen from JP Morgan AI Research, and we'll be talking to you about a bunch of research projects in the space of visual perspectives in finance. Before we get started, just a little tidbit about who we are at JP Morgan. The AI research team was a team set up a few years ago, and our mandate is to pursue research in the field of artificial intelligence, as well as adjacent fields like cryptography, and apply them towards building solutions that can help JP Morgan as a firm, as well as our clients. We're headquartered in New York City, but we also have offices in various other hubs around the world. The makeup of our team is individuals from a lot of different backgrounds. So of course, we have computer scientists and people from the field of AI, but we also have experts from physics, robotics, information theory, cryptography, and many others. To learn more about our team, feel free to visit us at jpmorgan.com/AI. So the research projects that we'll be covering are all motivated by taking problems in the domain of financial services and examining them through this lens of images or visualizations. So we're going to be doing a deep dive into one particular project that deals with time series forecasting via image prediction. And after that, Zhen will do a high-level overview of two other projects, trading via image classification and time series forecasting via video prediction. So the motivation of all of these works is that visual representations or visualizations of many sorts, they play a key role in the decision-making process. So if you think about a decision maker or a trader that's dealing with time series data, they're often leveraging plots and charts and all of these moving time series to make decisions about whether they should buy or sell a stock or if they should make particular deals happen. So the field of time series analysis and time series research has been very well studied. So we thought, why not reimagine this topic from the perspective of the end user or of the practitioner? So what we do is we create a system that can process these time series visually. And the benefits of such a system is that it's non-parametric and data-driven. And because we use images, they provide an inherent uncertainty estimate. Additionally, these kind of systems will have a huge advantage in use cases where you do not have access to the underlying data stream. So for example, if you have some sort of application where you can see visualizations of the time series, but maybe not the underlying data from which it's constructed, you could leverage the kind of methods that we're going to talk about. So this particular paper is titled Visual Time Series Forecasting, an Image-Driven Approach. The QR code on the top right will take you to a shorter version of this paper that was presented in a KDD workshop this summer. The full version of this paper will appear in iCubed, which is the International Conference on AI in Finance, later this year in November. So as a high-level overview, what we do is we take a bunch of time series that are visualized as images. In this case, the example refers to stock price history of the constituents of the S&P 500. And we split each image into two parts. So one includes the recent past, and the second image has a tiny overlap along with a segment of the future. Here it's painted in red, that we want the model to predict or forecast. So after we take thousands of these pairs and train a model, in our case, an autoencoder, we can query this model with new data and essentially predict the future. So for the purposes of our study, we chose to forecast time series using a convolutional neural net, in particular, an autoencoder. So we will refer to this method as the visual AE, or the visual autoencoder. So we deliberately picked a model that was simplistic. So of course, there have been a lot of advances in the field of deep learning, and we can leverage tools such as transformers, or maybe even LSTM cells to model recurrence in a time series. But we deliberately keep the model lightweight and simple, as we wish to examine the benefit of using images as a representation. So given that we have a neural network, a natural question is, how do you train it, or what sort of loss function you use? So on the right, you can see the image of a time series. And in particular, each column of this time series is one data point, and we treat that as a probability distribution. So when you plot any image, you will either have just one pixel, which is darkly colored, or you might have some adjacent gray pixels, either due to anti-aliasing or because you're trying to fit in a value into many discrete bins. So given that we can treat each column as a probability distribution, we can now construct a loss function that evaluates the loss between a ground truth image Y and the prediction Y hat in a column-wise manner. And since we're dealing with probability distributions, we can use something like the Jensen-Shannon divergence, which is a symmetric and more stable form of the KL divergence. So we use Jensen-Shannon divergence to train our neural network. Then in our experiments, we wanted to make sure that we're considering time series that are very diverse and not necessarily just from the realm of finance. So what we did was we constructed two synthetic data sets. The first was a harmonic data set, which is essentially a superposition of harmonics of different scales. So you will see that all of these images have some long-term trend, as well as a short-term trend playing out, as well as OU process data. So the OU process is a mean reverting process, where at each time point, the time series has a tendency to kind of stray away and do a random walk. But as time progresses, its probability of reverting to the mean keeps increasing. In addition to these two synthetic data sets, we also examined two real data sets. The first was the ECG data set from the MIT Sinus Rhythm database. And the last was the financial data set, which is daily close values of constituents of the S&P 500 for the past many years. On the right, you will see the same four data sets plotted out according to their complexity. Here, we measure complexity through a metric called weighted permutation entropy. So as expected, the OU data is the most complex, given that it's a synthetic data set. And the harmonic data set, because of its simplistic patterns, is the least complex. ECG and financial data fit in between, but as one might expect, financial data, which is often said to resemble noise, is highly complex. So now that we have four data sets, we also need to come up with some evaluation metrics to examine whether this method holds any promise or not. So two of the metrics that we use are from the realm of time series research. So the first is SMAPE, which is symmetric mean absolute percentage error. And the second is MACE, which is mean absolute scale error. For both of these, lower values mean better performance. And how we use it is once we come up with an image prediction, we can extract a numeric forecast by doing an argmax-like operation on the image. And then given that we also have numeric ground truth, we can calculate these metrics to come up with our error scores. Similarly, we also use two image-based metrics. But for these, we do not convert the image prediction back to numeric values. We simply compare our image prediction with an image of the ground truth. So the first is the Jensen-Shannon divergence, which is the loss function for our neural net. And the second is IOU, which is intersection over union, a metric from the object detection space. So please note that for all of these metrics, lower is better, apart from IOU, which we'll talk about now. So IOU in particular means that you come up with a union of the bounding box for any non-zero pixel. So in both your ground truth as well as the prediction, you can come up with the bounding box and see the intersection. So in this case, your IOU score is 1 because the intersection and union completely overlap. So one might ask, why use a metric that has nothing to do with time series, something that's used in object detection or image classification? And so I'd like to point you to the example at the lower half of the screen. So here you see one time series with 3 different predictions, prediction A, B, and C. So I would argue that at least visually, prediction C probably does the best job of characterizing the trend that will take place. So it says that this time series will increase in the future, followed by a subsequent decrease, which is what tends to happen in the ground truth. However, both prediction A and prediction B show just a weak increasing trend. However, if you now look at their scores, SMAPE and MACE, which are the traditional time series metrics, actually score prediction B as the best, with the lowest error scores, and prediction A next. So according to SMAPE and MACE, prediction C is actually the worst prediction out of the lot. However, IOU correctly characterizes prediction C to be the best one in this scenario. So along with using images to kind of model this whole time series forecasting task, we also wanted to use image-based metrics to see how you could diversify the lens with which you examine time series forecasting. So here is an overview of the results of our approach. So you will see our approach Visual AE highlighted in green on the left, and we compare this to 3 baselines. The first is a naive baseline, which we call random walk. This essentially predicts the last observed value with a growing uncertainty cone. So if you were to take an argmax, this prediction is simply a straight line at the last observed value, but the image prediction has this growing uncertainty cone. We also have numeric AE, which is simply a numeric equivalent of our visual autoencoder. So it is also another deep learning approach, but this does not convert time series into images and processes them directly. And lastly, we also have Arima, which is an autoregressive model, which is very popular in time series forecasting. So we provide 4 qualitative examples, 1 from each data set, along with the quantitative metrics on the right. So you will notice that our image-driven approach has these implicit probabilistic forecasts. So it can provide you uncertainty estimates without explicitly needing to estimate them. It's very good at predicting abrupt changes. So this can be noticed specifically in the ECG dataset, where the Visual AE does a fantastic job of recovering the spikes, whereas other methods fail to do so. And it's also just very good at capturing trends. So when looking at image-based metrics, Visual AE performs consistently well across all datasets, and also performs well in the other datasets based on some of the traditional metrics. However, we want to point out that for financial data, the traditional metrics such as SMAPE and MACE actually crown all 4 methods as the winner, which includes the naive random walk method. So this further goes to show how we can benefit from using image-based approaches as parts of our toolkits when it comes to analyzing and dealing with time series. Now I'm going to pass it off to Zhen, who will talk about some more work.
Thank you, Srijan. So for the sake of time, I'm gonna roughly talk about the other two selected projects along the same line of taking a visual perspective in finance. So this particular paper I'm showing here is one that was published in the International Conference at AI and Finance at 2020. The title is Trading Bio-Image Classification. And you can also feel free to refer to the top right QR code to have an access to the archive version of this paper. So the overall idea is that traders typically, work with visualizations of stock price, and there are, all kinds of visualizations of technical indicators and things like a candlestick chart to assist their decision-making process. Can we train a computer to do similar things? So for example, as we show on the left side, what if we take a snapshot of an image of, for example, like a candlestick chart of a stock price in a small window, and then train the computer to say, given that candlestick chart, what's the decision to do? So is it to buy, or is it to sell, or is it to hold? So essentially, this is a three-class classification problem. So during training, we have this sliding window that we generate different kind of snapshots of this candlestick chart over time. And we looked at S&P 500 constituent stocks. So in order to label the ground truth of saying, at different time point, is it to buy or sell or to hold, we use a technical indicator, which is very standard, called Bollinger Bands, which is basically plus and minus 2 times the standard deviation of the past 20 days moving average. So the idea is that if the stock price ever moves below the lower bound of the Bollinger Band and comes back in to the Bollinger Band, then that's a signal of saying, that's a chance to buy the stock, with the hope that the price is going to keep moving up. So similarly for the hold and sell. So using this idea, this is very popular deterministic strategy of determining when to buy or sell or hold, we use that to label ground truths to train a classifier, which is based on a CNN network, to decide the ultimate decision in the end. So at test time, as you can see on the right side, we're testing at Apple stock. So in 2018, and as you can see, the blue triangles are denoting the predicted buy signal from the trained model. The red triangle is denoting the true buy signal from our deterministic strategy. And as you can see across time, there are many coincidences between those two. So the predicted signal actually agree with the true buy signal most of the time. So you can see there are some false negatives where there are buy signal, but the model didn't realize it's actually a chance to buy. But overall, we achieved a high accuracy of determining what's the right decision to make. And in the next slide, we're going to show in more detail, what the performance looks like. So let me first explain what I'm showing on the left side. So this is about, taking a visual perspective in the finance. So there is a different way that you can visualize this data, right? So for example, you can use the candlestick, or you can just simply use a line plot with dots at different discrete time point of the stock price. And what we're showing on the right is if we're using these different kind of visualizations, do we get different performance? And the answer is yes, we do, but they are very similar. So let me explain really quick what's the x-axis of this plot on the right. So on the x-axis, we have 3 different kind of technical indicators that we used to come up with a deterministic strategy to label the ground truths. So earlier on the last slide, I explained basically how can we use Bollinger Band, which in short BB, to determine when to buy, sell, or hold. Similarly, we had other popular strategies that depend on technical indicators like RSI or MACD to decide when to buy, sell, or hold. So for each of this different data set, labeled through different technical indicators, you can see overall, the orange bar typically gives the best result, like the highest accuracy. And this orange bar, let me explain. So this orange bar actually corresponds to the visualization that we're using in the subplot B on the left side, which basically is the line plot with the closed data. So that basically means, like if you have the access just to the closed data, not even the open price, just having that is good enough to make a decent decision on when to buy, sell, or hold. So that's the overall result we would like to show for the trading by image classification paper. Feel free to check it out more if you're interested on arXiv, and we're happy to answer any questions at the end for this one. Moving on to the next selected project. So this is a recent work on deep video prediction for time series forecasting, also to appear in the second ACM International Conference on AI and Finance at 2021. Again, there's a QR code on the top right for you to access the archive version. So the overall idea is that, so far we've been talking about univariate time series. Can we predict univariate time series? Can we classify univariate time series? So when it comes to the cases where we need to deal with multivariate time series, how can we merge those information from multiple time series into one picture or one video, and then try to predict what's going to happen next? So that's what this paper is about. So this paper, for example, can jointly forecast the price change into the future of 9 assets together. So imagine you have 9 sets and you have this past history, the past stock price of those 9 assets, and you can look at the change of the price over time. So here what we're doing is that we're transforming these changes into a heat map at each time. Let's take the time t0, for example. What we're basically doing is that we calculate the delta price, meaning the price change in the daily data, and then the larger the positive delta price we observe, then the brighter pixel intensity we would put for that particular grid in this heat map corresponding to that asset. And the more drop of the delta price we see, the darker you will see. So imagine having this heat map for each timestamp, then over time, you're going to be able to generate a video of a 2D heat maps with different blocks lighting up or dimming. So imagine this, and then we want a computer to learn to predict what the future video frames are going to look like. Is a particular grid going to light up more? Is a particular grid going to dim even more? So the idea is that we can actually borrow the technique from computer vision and, particularly in video prediction that people use to predict human activity over time, and adapt that kind of algorithm into the domain of finance, into this kind of more artificial images other than natural images. And once we adapt those algorithms over, we can predict the future video frames. And again, these kind of algorithms are typically still more based on CNN as well, but also combined with LSTM. So in the end, once we predict the future frames, as you can see on the right side, what we're doing is that we can map those pixel intensities again back to the original delta price domain, so that we know whether that represents the price is going to go up or go down for particular different assets. So in particular, we tested on the year of 2019 based on training data from 2010 to 2018 on those 9 assets. Next slide, please. Thank you. Yeah, so here is just like a high level showing our overall results. So basically the video 4 is the one that we propose, and video int stands for video individual, and video shuffled are the variants of our method. So in particular, video int stands for what if we just learn this for each asset individually without learning them jointly in a 3x3 grid heat map. But instead, we just have one single information for each asset at a time. And video shuffled represents, as we show on the bottom left picture, video shuffled represents another kind of layout, spatial layout of those 9 assets by randomly shuffling them around and having actually interdependent assets being more apart from each other in the image compared to the video full. So what happens as expected is that, you know, like with those interdependent assets being more distant from each other in the 2D image, it was harder for the network to capture those dependencies and thus actually achieving a lower sun accuracy as a result. So I'm going to go into those comparisons between different methods just in a second. So the next baseline we looked at is video deep insight, which take some ideas from a clinical study work that try to transform patients' data, which are typically non-image data, into a kind of an image, and then use that to classify whether a subject has a tumor or not, like mainly for medical diagnosis. But we adapt that into our domain as well to do the forecasting. Also tried, to see whether that brings us any edge on doing the time series forecasting. In addition to that, we also include Arima and Profit as the standard ways of doing time series forecasting using the regional time series data, in numbers, basically, other than the images. So overall, what we're showing in these bar plots is for each one of those 9 assets, you can see the sign accuracy that we're achieving for the very next day prediction. For video full, that typically gets the highest accuracy, almost for all the assets or on par. And other methods don't really, achieve as high as sign accuracy. So this is like the key takeaway for us is that, using this video prediction kind of technique can help us learn jointly to predict a multivariate time series, which actually succeed, outperform those time series forecasting methods in the original numerical domain. Next slide, please. Yeah, and that concludes the selected projects on the visual perspectives in finance. Now I'd like to talk about the external engagements that we're having, particularly with DSI at Columbia, and the opportunities for collaboration. So ever since fall semester in 2019, we have been actively mentoring students through DSI capstone projects, and now we have been interacting with 50 plus students so far. Just to name a few, these are some ongoing data science capstone projects that we have, like, for example, hierarchical time series forecasting. There's also graph machine learning for mixed data sources, and another one on assistive robot to recognize and engage with people in need. And we definitely look forward to continue this effort and keep interacting and learning together with all the students through the future DSI capstone projects. In the meantime, we also have faculty research awards and PhD fellowship awards each year. So here are a quick list of the professors and students that we have close collaborations with over the years. Next slide, please. Thank you. Yeah, and we have also an upcoming conference on international conference on AI and finance happening really soon in November 3rd. So if you're interested, please check out the QR code on the top right and see if there's any, papers you're interested in, any topics, any invited talks you're interested in. Feel free to register and join us. There are also several workshops that we're also hosting at the conference. One on time series, the other 2 on women in AI and finance, as well as AI in Africa, and another one on explainable AI in finance. Next. Right, so last but not least, we have many job opportunities in JP Morgan, not just in AI research that Srijan and I come from, but also in a broader, departments across the company. So I just want to particularly mention this upcoming opportunity from JP Morgan, which is a series of programs that aim to have an early chance of having an early engagement with the students within our data scientists, researchers, and quantitative modelers through this series of summits. So for example, on December 4th, we're going to have the 2022 AI Research Summer Associate Program. And then following up on that, we're going to have the other two programs that are for a broader department, not just AI research. So this actually covers other kind of department, like, for example, applied machine learning and quantitative research and asset management. So if you're interested, please check out this link here. And again, the QR code on the top right will take you there as well. We can also share this link directly with Jessica so that she can forward that to all of you. And of course, there are also full-time positions. So please check out our career page. There are many, interesting openings right now at our team, looking for, either general research associates, but also, explainable research scientists. So that concludes our talk today. We're happy to take any questions from the audience.
Thank you so much. Yes, if anybody has any questions, please feel free to pop them into the chat. Oh, someone's asking for the barcodes, the QR codes. Yes, so we're happy to share that again. Yeah, let me see if that works. There we go, for the job opportunities. Also, we're happy to, if you send these over to us, we're happy to distribute them as well. With John Hyde and Taylor Reyes, we're distributed to our students. It'd be wonderful. So speaking of recruiting and job opportunities, it would be wonderful to hear from both of you about what like an ideal candidate would bring to the table if they wanted to join the AI research team.
I can go first, and Srijan, feel free to add more. So I can speak from my own perspective. So I think what we're looking for are definitely talented people, but also like people that would like to have fun in AI, and then bring, and also bring their different perspectives based on their background, their experiences into finance. So we're not necessarily like asking for super strong financial background, which could be a plus. But honestly, for example, me personally coming from a robotics background, I had not much knowledge in finance, but I'm interested. And I have an extensive experience in AI and in robotics. So taking that kind of, way of formulating problems, for example, with AI mindset into the finance is something that we're looking for. So if you are interested in, machine learning, deep learning, in AI in general, I mean, we have many opportunities.
Yeah, I agree. So I'd say most important is probably the curiosity aspect, right? So as long as you're curious about solving problems in the space of financial services through this particular AI mindset. And then second is the opportunity to publish. Right? So if you're interested in a career in research, so that means carrying out these projects end to end and then writing about them and kind of disseminating them in academia, that's also a huge part of the job. So particularly for AI research, it's not just it's not just projects in production. It's kind of, we zoom out a bit more than that. But I think there will be relevant opportunities depending on the team for every person.
Thank you. A question that came in is, can international students apply for summer internships?
I believe so, yes.
Oh, wonderful. And another question that came in, a student applied for a position that didn't work out, but are they able to apply for other locations as well, such as in quant and data science specific positions as opposed to just AI research positions?
Yeah, I don't think that should be an issue because those will probably be considered as individual tracks. So I'd say one of the best bets would be to maybe join in on the networking summits that Zhen spoke about, the virtual AI and quant modeling summits. And that would kind of give students a first-hand opportunity to network directly with both practitioners and recruiters.
Wonderful. Is there any result metrics from speed efficiency of forecasting time series with CNN? What's the potential of the method in industry adoption, especially for high frequency trading?
Yeah, so that's a good question. We
Great
did
question.
not necessarily do any analysis into the speed and the latency effects of these predictions. But yeah, if it comes to deploying them in high frequency trading systems, that would be a very important consideration. But it's not something we've looked into, at least in this study, just yet.
Well, that's that creativity, right, students? You hear? Do you have any teams using reinforcement learning or causal inference?
Yeah,
Yes.
so our team has plenty of projects. In fact, we have a couple of papers from our team that will be present both at iCubed as well as NeurIPS this year that utilize reinforcement learning in many different settings, along with, I think, a couple of causal inference projects. And there's actually one that combines causal inference and reinforcement learning. And I'm sure that there are also teams that are not AI research. So some of the applied teams at JP Morgan have also leveraged RL.
Yeah, and if you're interested, we have like a publication page on the JP Morgan AI research, and you can check it out. I believe we keep that up to date. So any recent publications will be out there. There is a recent one on reinforcement learning, and there were past ones on reinforcement learning as well.
Thank you. Yes, that's a wonderful resource. So we do have another question. Why do Arima models perform badly? And maybe for the next time, it would be interesting to compare that knowledge with the human trader use.
Could you repeat? Okay, wait, let me. Okay, I see the question. So I think so the question is why do Arima models perform poorly, right, when it comes to this particular time series forecasting problem? I think it boils down to how much Arima's limited success when it comes to seasonality. So of course, there are more recent models that, for example, Profit or Neural Profit and other extensions that look into explicitly modeling seasonality. So I'd say maybe that is one component. Apart from that, I think it would be the fact that Arima focuses on linear trends. Zhen, anything to add in that space?
Yeah, Arima is definitely mostly linear operations. So if there is any nonlinear dependencies over the time, then Arima is gonna have a hard time capturing that. The other quick point I want to mention is, so typically Arima will be applied on a long time series that you train on, and then you just keep predicting, right? Or at least when you are making the prediction, you have certain past history to feed into Arima model so you can make predictions. For us, like the setup is more like we only have a snapshot, which is relatively short time frame, like a snapshot of the past history. It's not like going all the way back 10 years, and then using that to feed to Arima. So that could also affect the performance of Arima, because imagine what in practice what happens is that you train Arima, let's say on eight years worth of data, and then you randomly take a snip in let's say 2019 and put that into Arima with only, let's say, 80 data points. Then from the Arima's perspective, it's almost like those 1 year in the middle is completely missing. So it's going to be challenging for Arima, and it's actually the same case for Profit as well, to make a good prediction in that case. So for us, the way we trained our model is that the only thing we need is that snapshot. and the model tried its best to make the prediction given that limited knowledge. So I would say that's more because of the way it was trained, typically the way how it's expected, how it's deployed in practice. So definitely our model, in cases where you have limited knowledge or you have limited past history, our model is going to be able to give you better performance.
Thank you. We have a question about internships. At JP Morgan, do they require a student to graduate in a specific month year?
I don't think so.
Yeah, I think it would depend on what kind of internship position. So we have a couple of different ones. So the summer analyst program is catered more towards bachelor's, and then the associate program is catered towards master's or PhD. I think depending on the specifics, this is a question I think the recruiting team will probably be able to answer the best. So based on a student's particular situation, one program might be a better fit, because I'm aware that for certain master's programs, they actually recommend the analyst program based on your graduation date. So yeah, I think a recruiter will be able to help with that.
Yeah, but I think we do have the flexibility to accommodate different different time of the year for the graduation.
Thank you. So follow-up question. In your presentation, you mentioned accuracy. How do you define accuracy in this context? And are you using any of the common regression evaluation indices such as MAPE, AMSE, etc.?
Which project is this referring to? Is it the time series
Professor
forecasting?
Arya, if you could let us know which project you were referring to. The time series, please. The time series project.
Okay, so we have two. One was the image one and one video. I guess we can just cover both.
Yeah.
So do you see my screen?
Yes, we do.
Yeah, so for the image-based approach, we do compare the numbers for all of these metrics. So in particular, the way we calculate these is right here. So we compare it to SMAPE and MACE. But I'm guessing since we didn't explicitly use the term accuracy here, the question might be about the video project, and in particular, maybe sign accuracy. Zhen, do you want to take that?
Yeah, I can jump in really quick to explain what I meant by sign accuracy. So basically here, the goal is to predict, whether the price is going to go up or down, let's say for the next day. So sign accuracy basically means if we predict, next day the price is going to go up and it actually does go up, then that's, an accurate guess. Then if it's the opposite, then we have a bad guess. So that's basically how we evaluate the sign accuracy. This is the main metric that we considered in this study. We didn't include the maze or SMAPE, for example, as we did in the other study. The main reason is that, for this one, the heat map has somewhat, the expressivity of the heat map is not as rich as the one we had in the image, where you have, almost like one column to decide where the price can go. So for this one, it's more like brighter means going up, darker means going down. So for us, we're mainly just focusing on the price movements itself. But definitely in the future, if we can make this representation richer, we can definitely include those time series metrics as well.
Thank you so much. Another follow-up question. Srijan, do you know the name of the paper that combines causal and reinforcement learning you mentioned earlier by any chance?
So I think for that one, I'm not sure if it's past the camera ready stage just yet. So
Okay.
I'd advise you to look at our public website. So as soon as it's past the camera ready stage, our team will update the accepted paper, and you'll know it when you see it.
Great. So students, make sure to keep up with that website. So our next comment or question is from Stephen. He says, I guess that there may exist some covariate shifts within the whole time scale of training data. Is this phenomena, if this phenomena exists, I guess some kind of setting like transfer learning or continual learning may possibly improve the performance? This is a question.
That's a very great point. So far we haven't looked into that aspect as much. But I do think there could be there probably even is covariance shift in the, because we're looking at, 20 years or 10 years of data. So that definitely is an idea. And trying to train, over time and improve over time. The only issue right now is really the data. So because if we continue learning over time at the beginning, each year, honestly, like if we are using daily data, we don't have much data points to leverage, for a deep learning paradigm. So that's like one issue. But of course, if we can do like collect more data, not just S&P 500, expand it to a lot more stocks in the market, that could be becoming a more a possibility. And Srijan, feel free to add more.
Nope, I think you covered it.
Awesome.
So I always take advantage of the opportunity to ask our speakers how your path to being data scientists came about. Like, we know not everybody's path is linear, and I think it's really informative and wonderful to find out how you ended up on the AI research team at JP Morgan.
Sure. So Zhen, would you like to go first?
It's okay, you can go first.
All right. So my background, I'd say, is fairly traditional. My undergraduate studies were in computer science, and initially, as the tradition is, every summer you probably do an internship. So my first couple of internships were on the software engineering side of things. And then at one particular company, I got involved in some machine learning engineering projects. And that's when I kind of realized that I do have an interest in data science and machine learning, which kind of led me to pursue an undergraduate thesis. So as a part of that framework, I realized that I do like research. I like pursuing these open-ended problems and then the entire process of writing about it. So I kind of continued that along. So my fields of study later on in my master's degree, I was pursuing reinforcement learning and fairness in machine learning. So I was involved in multiple different research projects with various different faculty members at Georgia Tech, which is where I come from. And I think that kind of reinforced the fact that I like data science and machine learning. So in that sense, it was fairly traditional. And that's how I ended up at AI research at JP Morgan.
Cool. Yeah. So as I mentioned earlier, I actually come from a robotics background. So I'm not a traditional data scientist. So but the connection I see is that, like in the past during my PhD, I mainly worked on robot perception, so like making the robot see through the world with its sensors, like cameras. So I deal with images, videos, and then make the robot understand, objects and people. So, and then I didn't really, know about AI research because it was like in a very early stage. But Manuela, who is the head of AI research, actually came to our university and at University of Michigan and gave a talk about what they're doing at AI research at JP Morgan. So I went mainly regionally mainly because Manuela is well known for her contributions in machine learning and robotics. So I went, but I was expecting actually a standard talk from, I don't know, banking industry or quantitative research, for example. But actually I went and I heard something that I didn't expect at all. So it was like really interesting, and all the projects she was presenting were very fascinating. So that's like the point where I start to think I don't necessarily need to, like only think about just doing robotics. So there are many other things out there. And taking this, and obviously Manuela is able to think, look at these problems in finance with her experience back in machine learning and robotics. Maybe I could do the same. So, but I also think those projects seem very interesting. So that's why, that opened my basically chance of actually start thinking, start applying. And then the more I talk to the people at the team, the more I, feel that this is a good place to be. And after joining, and as you can see, I'm involved in this visual perspective in finance, which align really well with, my background. And so it's a very nice, I would say, connection from my background and into the financial world. Yep.
Wonderful. Thank you both for that answer. It's really interesting. One other question that I ask is, if our students who are right now in the program, what classes, what skills would you really recommend that they make sure that they have under their belt by the time they leave our program?
Programming to begin with.
Okay, yeah.
But I think all the students probably are going to be prepared by the DSI program. But I think but just share 2 cents from my side. It's programming skills like Python or C++. That's the mainstream. I mean, Python is definitely used more in industry, I think. And like machine learning and some familiarity with deep learning concepts, like different type of models like CNN, RNN, like to deal with different type of data with different nature. What else? And maybe some that it's not about course per se, but maybe some experience in like leadership could help, right? So like being able to lead a team on a some project doesn't have to be a super research intensive project, but a project that could also be a plus on the resume, let's say.
That's awesome. Thank
Yep.
you. How about you, Srijan?
I'd say probably the fundamentals in probability and statistics go a long way. So that's something I think I personally overlooked back in undergrad. Of course,
Okay.
you take a course. Back then, when you're an undergrad, the objective is to get an A and move on. But I think for a data science or machine learning practitioner, those fundamentals go a long way. And then I think the field is pretty broad, that everyone ends up picking out their own specialties, right? Whether it's natural language processing, robotics, computer vision, and there's so many. I think regardless of what specialty someone picks, it's important to either take courses or participate in projects that kind of get your hands dirty, and in specific, building something from scratch. So I think that there's I think a ton of tutorials on using a library to do some plug and play analysis, but being able to build something from first principles, just from the very basics. So for example, if that thing is deep learning, if it's about building neural networks, of course it's great for someone to learn how to use PyTorch or TensorFlow or one of these frameworks, but it's very important to maybe try building out your own convolutional neural network just using NumPy, right? And I think that really helps you understand the fundamentals, right? Why things work, and more importantly, why things don't work. And those kind of learnings really resonate with you later on.
Yeah, and just following up on that, actually also like linear algebra would be a very fundamental thing also, just to get familiar with. There's like a fantastic book, like a little book just called Linear Algebra, that you can buy easily on Amazon. And you might find yourself refer back to that book from time to time. The other thing is that's like one thing I realized recently. I think so far there are so many like projects that are out there where you can just grab the data easily. So there are public data sets that are available and they're clean and they're processed already. You just take them and then you apply a model. But actually in reality, in real world, when you start a machine learning project, you need to really think about what is the goal? How would you collect your data? What kind of filtering, what kind of procedure you need to go through for those data collection. So I started to realize recently that might be something that's lacking during the courses, could be. So if there are some course projects that are handed to the students just with like the data being ready, the students might not have the chance to really try to collect on their own. But actually that's a very important first step for a machine learning project. So like Srijan mentioned, not particularly which course, but like this kind of skill or this kind of experience of getting your hands dirty from the very beginning of machine learning project will be nice.
Awesome. Thank you so much for the insights and the tidbits. It was a linear algebra book that's on Amazon. You said it was a small one?
Yeah.
Okay.
Yellow blue thing, like this, like not big. Yeah.
All right. It's going to be sold out after the end of the time. Okay. Well done right now. We have time for maybe one more question. It just popped in. Not sure if someone asked this question, but you noticed that for AI and DS full-time, oh, this is more of a campus thing. So I'll leave that question for John Hyde. We'll leave that question for John Hyde. I'll copy and paste it and we'll send it over to him. But I want to thank you both so much for your time. Thank you for all your work that you are doing with our capstone projects. Everyone, if you're not in your final semester right now, please look out for projects that JP Morgan puts out in the spring and hopefully next fall as well. They're always so interesting and engaging, and our students walk away with like a wonderful experience. So we thank you so much for all your participation and engagement with us on that level as well.
And thank you for having us. It was a pleasure being here, and it's a pleasure interacting with the Columbia community.
Yeah, and thank you for all the wonderful questions.
Thank you, everyone.
Really quick thing before we wrap up.
Yes, please.
Can you Jessica, could you forward like our contacts to the students? I think like some students are probably trying to reach out to us individually, like directly. So I want to make sure they have the contacts before we end this meeting, because I see like a message trying to connect, but I don't have the contact.
Sure. You know what? I can definitely pop both of your email addresses into the chat, but I can also, Alexis, are we able to forward like the people who registered for the talk? Are we able to also provide them this information in a follow-up?
Yep, I can do that. I can send it out via Eventbrite, so everyone who registered can get their email addresses.
Great. We're gonna do both. I'm gonna pop this in here and then in the chat, and then we'll make sure to follow up with all that information afterwards, especially, and also including the video. This has been recorded and we're gonna be happy to share it. So many insights in this one. We appreciate it.
All
right. Thank you, everyone. Have a good day.
You too. Take care.